So today we're going to talk about some of the more powerful results of logical inquiry in the 20th century. Undecidability relates to limits in our ability to mechanize our processes of proof and therefore of discovery. And incompleteness relates to our ability to prove, whether mechanistically or not, everything that is actually true. So we'll begin by reviewing some of our basic concepts and then talk a little bit about both of these interesting results. So almost everything we've been doing in this course is logic. When you're doing logic, you're typically using it to demonstrate that its woofs have certain properties such as logical consistency or deductive validity or derivability. Metalogic studies the general logical properties of the languages themselves rather than the specific propositions formulated within them. So some metalogical properties have the same names as logical properties. For example, we can speak of a set of sentences as being logically consistent in the sense that they are free from logical contradiction. But we can also speak of a formal language as being consistent, either with reference to its semantics or its proof system. A formal language is consistent if it is impossible to prove some formula A in its negation, not A. Since in classical logic you can derive any formula from a contradiction, standard way of expressing freedom from contradiction is to say that there is some formula that cannot be proven. So to understand these properties, it is helpful to once again review the fundamental distinction between semantics and proof. In logic, when we spell out the semantics of a formal system, we are spelling out the conditions under which the propositions we can formulate within that system are true or false. Remember, semantics is about meaning, and in logic we explicate the notion of meaning, like the meaning of a sentence, as the conditions under which it is true or false. Now, in propositional logic, this only requires reference to truth tables, but in predicate logic, this requires reference to models in which names and predicates are given specific interpretations. When we're doing semantics, we are fundamentally interested in the conditions under which particular woofs of a language are satisfiable. A formula is satisfied in a model if it is true in that model. A formula is satisfiable if there is at least one model in which it is true. So, for example, if F means funny and C means Charlie, then uppercase F, lower c, FC, is satisfiable if there is a model in which FC is true. Logical contradictions like FC and not FC are not satisfiable in classical logic, since when FC is true, then not FC is false. And by definition, a conjunction is only true when both conjuncts are true. We also talk about arguments in purely semantic terms. Arguments are just lists of woofs, one of which is identified as a conclusion. When we inquire into the validity or invalidity of arguments, we are still doing semantics. This is something that isn't necessarily emphasized when you take a beginning logic class. We often talk about proving that an argument is valid or invalid. But if you're actually using the proof procedures of a formal language, you're not technically demonstrating validity. You're demonstrating derivability. So when we use trees to test the validity of an argument, we're still technically doing semantics. Trees are a semantically based procedure for determining the validity of formulas and arguments. Proof theory doesn't, as I just said, concern validity. It concerns derivability. A derivation is different from a semantic test for validity in that the derivation rules are used to generate or derive a conclusion, whereas trees and truth tables can only establish validity by exploring all possible interpretations of the formulas involved. Proofs derive conclusions strategically through a judicious and sometimes creative application of the available rules. Proof is essentially meaningless. It is ultimately just a set of rules for manipulating uninterpreted symbols. This is fundamentally how computers work. Computers, as currently conceived and constructed, are just symbol manipulators that do not themselves seem to have any understanding at all. Now, whether this is correct or not, or whether it must be correct or not, it is the fundamental distinction between semantics and proof that grounds this kind of claim about the limits of computers. Now that we have reminded ourselves of the distinction between semantics and proof, we can state how they are supposed to be related. Ideally, we desire that every proposition and argument that is valid, semantics, be derivable, proof. In other words, it's a serious cause for concern if, in a particular language, we can know on semantic grounds that a formula is necessarily true, but we're not able to derive it. Conversely, it would be alarming if we were able to derive a formula that is semantically invalid. With this understanding in place, we can now dial in the precise meaning of some of the basic metalogical concepts that relate semantics to proof and vice versa. So that we can state them precisely, recall that when we are doing derivations, what we prove are called sequents. This is a sequent for an argument, two premises, and a conclusion. This is a sequent for the very same argument represented as a theorem, right? So in the first case, we have premise P or Q, the second premise not P and therefore Q, and this is essentially equivalent to the theorem: if P or Q and not P, then Q. If you can prove the first, you can prove the second using our method of conditional introduction. So in the first case, the sequent is derivable if and only if Q can be derived from the formulas P or Q and not P. In the second case, the sequent is derivable if and only if the entire formula can be derived from no premises. We have noted that every valid / derivable argument, such as this, P or Q not PQ, can be rewritten as a valid formula like this. In discussing logical properties, it is helpful only to speak of the latter, so that is what we will do. First logical property we'll discuss is soundness. Now, a logical system is sound if and only if every derivable theorem is valid, which we may represent for mnemonic purposes as if D, then V. If derivable, then valid. Now, soundness is considered the most basic desirable property of a formal language. This is partly because it ensures logical consistency. If a language contains contradictions, then anything can be proven, as we noted, and including sequence that are invalid. Completeness is the inverse relationship. A logical system is complete if and only if every valid formula can be derived. Whereas soundness is a condition of minimal acceptability, completeness is regarded as a highly desirable virtue. It basically tells us that if a formula is true, it can be proven. Importantly, completeness is only a serious accomplishment if the system is consistent. It is a trivial accomplishment if the system is inconsistent, since in that case, all formulas are derivable. Trivially then, if a formal system is both sound and complete, then this follows. Formulas are valid if and only if they are derivable. And that is really the bee's knees when we are talking about formal systems. So, decidability is the other property that's very important to us. And this is a horse of a different color. It is not just about the relationship between the semantics and proof apparatus of a language. A logical system is said to be decidable if and only if there is an effective method for determining for any proposition whether it is valid or invalid. This is also the technical definition of an algorithm. What we mean by an effective method is whether it can be fully mechanized so that no human judgment is required to demonstrate it. Although some proof systems can be made into effective methods, their practical value to us lies in the fact that they offer the opportunity to derive a result strategically rather than involve us in a comprehensive search of all logical possibilities. That's what computers are very good at. It's what humans are not good at all. Refutation trees in propositional logic are effective procedures. They are completely mechanical algorithms that can be used to determine the validity or invalidity of any formula in propositional logic whatsoever. Since refutation trees, or truth trees as we often call them, are not part of the proof apparatus, this is one way of remembering that decidability isn't inherently a relation between proof and semantics. Decidability is a very important property, however, as it relates to what sorts of results can and cannot be reliably performed by a computer. Propositional logic has all of the virtues listed above. It has been proven to be sound, complete, and decidable. But propositional logic achieves all of these virtues partly because of its limited ability to capture logical relationships. For example, you cannot show in propositional logic that a sentence like everybody is happy and nobody is happy is contradictory. In propositional logic, this sentence just has the logical form A and B. Earlier in the semester, you might have done a double take when I said this because it wouldn't have been perfectly obvious. Why couldn't you, for example, just say that everybody is happy is A and nobody is happy it is not A, right? A and not A. but you know the reason why that's not the case. Not everybody is happy says it's not the case that everyone is happy, and that's different than nobody is happy. So in predicate logic, you can show that such a sentence implies a contradiction, but this extra power comes at a cost. The cost was discerned in 1936 by a fellow named Alonzo Church, who showed that while predicate logic, including identity and function symbols, is sound and complete, meaning every validity can be proven and everything that can be proven is valid, but it's not decidable. And that's something we saw early on when we extended our truth tree system to predicate logic. So to review what we saw, trees in propositional logic provide an effective procedure and algorithm for determining whether any formula is valid or invalid, but trees in predicate logic, though they're very useful and will always return a result for valid formulas, there are certain types of invalid formulas that get them into an infinitely repeating loop. For example, this is an invalid argument. The argument being for all x there exists a y, gxy, therefore gbb, which of course we could also just represent as a potential theorem. And essentially, because of the placement of the universal in the existential quantifier, we are forced by our procedures to continuously reinstantiate the universal after a new instantiation of the existential. So in computer science, the problem of decidability is known as the halting problem, and it was shown to be unsolvable by the famous British logician Alan Turing. It's a serious computational limitation since at any given time, you cannot tell with certainty whether the computer is working to find a proof of a valid sequent or just looping infinitely on an invalid one. And even if a human can tell, it is obviously far better if a computational process does not depend on human judgment in this way. Still, because predicate logic is complete, meaning that every valid formula can be proved, it might still be reasonable to hope that set theory and mathematics are complete as well. Or at least this belief would have been plausible if it had not been disproved 5 years earlier. In 1931, Kurt Gödel had already demonstrated the incompleteness of any logical system powerful enough to do basic arithmetical operations. Gödel's result put an end to what was known at the time as the Hilbert program, named after David Hilbert of Hilbert Hotel fame. The aim of this program was to show that mathematical knowledge could be put on the sort of bedrock foundation that philosophers had long sought to provide for all of human knowledge. The central desideratum of the program was completeness, the demonstration that all mathematical truths were in principle provable. Gödel's proof is very complicated, and it is not possible to summarize it without running roughshod over lots of important distinctions and concepts. For example, one important point is that the relevant notion of completeness involved here is a little different from the one we defined above. The concept we defined above is sometimes called semantic completeness, and it specifically applies to valid formulas. To see the importance of this, recall that in predicate logic, most formulas and their negations are invalid. This is true in propositional logic too. Your average woof, as well as its negation, there's some examples, is what we would otherwise call contingent. Both are satisfiable in some model or another. Valid formulas are true in all models, but only a subset of invalid formulas are false in all models, namely formulas that are equivalent to the negation of valid formulas. So mathematical contexts are different. In mathematics and set theory, every proposition is either necessarily true or necessarily false. There is no model that satisfies the proposition that 2 is greater than 3, or that the set with the elements 2, 3 is a subset of the element of the set that contains the element 3. Hence, as a result, we are entitled to much stronger inferences than in predicate logic proper. Specifically, for every formula A that is not valid in a mathematical context, its negation, not A, is valid. And that's very important. Church showed that predicate logic is undecidable in spite of being complete. The completeness of predicate logic was proven actually by Gödel. In other words, even though we can prove any valid formula valid, there is no effective procedure, no algorithm for determining which formulas are valid and which formulas are not. With any such procedure, there is always going to be some point where it gets stuck in an infinite loop trying to work out whether an invalid formula is valid or invalid. However, the completeness of predicate logic essentially implies that it is semi-decidable, and sometimes called recursively enumerable. In other words, since we can prove every valid formula, there is a decision procedure for determining whether any valid formula is valid. Now that procedure would simply involve enumerating all of the proofs and going through them until we find the ones we're looking for. What I mean here is when we're doing proofs, when humans are doing proofs, we're not doing it mechanically, we're doing it strategically. There are all sorts of ways that you can derive a conclusion even in the simplest proofs. So one sort of cheap way of creating a decision procedure for determining whether any valid formula is valid is just to get all the proofs done, put them in a list, and have the computer consult the list whenever it's supposed to determine whether a sequence is valid or not. So in mathematical context, this semi-decidability is effectively decidability. The reason, as we explained above, is that in mathematical contexts, all propositions are either necessary truths or necessary falsehoods. Hence, if a formal language representing mathematics were complete, there would be a decision procedure for determining whether any formula or its negation is valid, and hence whether any formula at all is valid. Gödel's proof relies on a technique he invented called Gödel numbering. Gödel numbering is similar to ASCII or Unicode, which assigns integers, ultimately in binary, to specific characters. This allows us to Gödel number entire formulas, such as there exists an x, such that x equals SA, the function. And it would look something like this. each symbol is assigned a number. Now, Gödel numbering goes further than this, however. Specifically, it represents every woof as a single number, specifically as a product of the first n prime numbers raised to the power of the Gödel number of the character. So prime numbers 2, 3, 5, 7 are assigned in order, the order in which the symbols occur, and then those prime numbers are raised to the power of the symbol that indicates the number, and then these are all multiplied to get a single unique number representing that formula. So, of course, a huge amount of Gödel's work was in inventing this technique, was to show that this actually works, that unique numbers necessarily result from this procedure. So this process assigns a unique number to each woof. It also can be used to assign a unique number to sequences of woofs by raising successive primes to the Gödel number of each woof in the sequence. Right, so if you want to represent sequence rather than formulas, you take the Gödel number of a formula and simply reapply this procedure as if the sequence were just individual symbols. The ultimate result of Gödel numbering is that it arithmetizes metalogic. The way it accomplishes this is that statements about logical formulas and sequences of logical formulas are true if and only if specific mathematical relationships relating to the way that Gödel numbers were constructed hold. To take a trivial example, if we wish to say of the formula, if P and Q then S, that P and Q is the antecedent condition, this could only be true if the Gödel number of P and Q is one specific factor of the entire formula. The genius of Gödel numbering, one that this sort of superficial and sketchy exposition can't help us to appreciate, is that it makes it possible to assign a number to any proposition or sequence of propositions we like. For example, we can use a single number to express a statement like the sequence of formulas with Gödel number A is a proof of the formula with Gödel number B. In order to think about this formula clearly, let's cheat and represent it in the object language symbolically as A is a proof of B. The important thing to notice about a statement like PAB, A is a proof of B, is that it has a truth value and therefore clear arithmetical truth conditions in the Gödel numbering system. Specifically, PAB is true if and only if proves is a relation, a mathematical relation, described by a particular Gödel number that holds between the Gödel number described as A and the Gödel number described as B. So the Gödel numbering system also allows inference in both directions. We can infer the Gödel number of the full metamathematical expression of PAB, and we can infer from PAB its full metamathematical expression. Finally, Gödel's system also allows him to describe logical operations mathematically. For example, the use of the predicate logic rule, universal elimination, as follows: will itself be describable as a purely mathematical operation involving the Gödel number of A and the Gödel number of, for all x, pxa. Of course, it isn't a simple mathematical operation like subtraction or division, but the point is that it's just math. So let's let this formula for all x not pxu say something that is sayable in Gödel's system, and that is that there is no Gödel number corresponding to a proof of the formula whose Gödel number is U. In other words, this says for all x, it's not the case that there is something that proves U is unprovable. So, right, all we're saying here is that Gödel has developed a system for getting any system capable of representing basic mathematical relationships to say of itself various things. And one of the things it can say is this: for all x, it's not the case that x can prove this formula. Now, of course, this very formula has a Gödel number, and you can probably guess what it is going to turn out to be. That's right, it's U. Now, of course, the point is not that any formula that says there is no proof of A is going to have A as its Gödel number. The point is that Gödel proved that there will always be formulas like this. There will be formulas with a specific Gödel number, and the formula itself says this formula cannot be proven, which is what this says. This formula effectively says I cannot be proven. And this is directly analogous to the liar's paradox, which we've discussed in the past, where an individual human being says, I am lying. So we can brace ourselves for a kind of paradoxical result. But this time, it's not going to be paradoxical. It's going to actually prove something very important. So if you isolate one of these formulas, a formula whose Gödel number is, in this case, U, that says of itself that it cannot be proven, something very interesting follows. So using this method, Gödel was able to construct this formula that effectively says of itself that it cannot be demonstrated. The general way in which this particular self-referential formula is produced is not actually that hideous to grasp, but we're not going to pursue it in this discussion. Although the self-referentiality of this expression, again, we'll just keep repeating it, gives it the paradoxical flavor that we have observed in the Russell paradox and the Burali-Forti paradox, it is not clearly paradoxical. In a consistent system capable of representing the truths of arithmetic, no arithmetical falsehood can be proven. So we might just suspect that as long as U represents a falsehood, then there is nothing even that interesting going on here. So that's fine for the moment. At this point, Gödel seems to have given us this funny formula that refers to itself. Again, for all x, it's not the case that x proves U, together with the claim that the formula is either true or false. The thing is it turns out that either way he will have made his point. Why? Well, if U does represent a falsehood, then it is false that U cannot be proven, which of course is to say that U can be proven. But this also means that the denial of U, right, so take U and negate it, and then go ahead and apply quantifier elimination, right? So the denial of U is just the claim that there exists an X such that X is a proof of U must be true. In other words, there exists a proof of U even though U is false. So let's just go back through this reasoning again. Originally, we're just looking at the original Gödel formula, which has the Gödel number U, and it's for all X. It's not the case that there is a proof of U. And our response is, well, so what? That's probably because U is false. We would not want to be able to prove U if U is false. But in this case, if U is false, then its negation has to be true. And of course, not just in this case, but any case. If a formula is false, then its negation must be true. And when we negate the Gödel formula, we get the claim that there does exist a proof of U. But if there exists a proof of U, when U is false, that is a very bad thing. You do not want to be able to prove things that are false. In a mathematical context, if you are proving falsehoods, you are proving logical falsehoods, and so the system is entirely broken. In other words, mathematics ends up being completely inconsistent. So Gödel's true result gives us two options, both unpleasant. Either mathematics is inconsistent, or there are truths that cannot be proven, i.e., mathematics is incomplete. So Gödel demonstrated the necessary incompleteness of any formal system, any consistent formal system, capable of representing all the truths of arithmetic. He did this by proving that in any such system, assuming it is consistent, there will always be a rather strange self-referential formula that is both true and unprovable. Although this result is philosophically very important, it does not entail any essential unreliability in mathematics, so long as we know to avoid formulating propositions like this. In that respect, it is a lot like the liar's paradox, which we can capture by simply giving a name to a very weird sentence. S is false, as we described before. If we call S the statement that S is false, this sentence is true if and only if it is false, plausibly showing that truth itself is a paradoxical concept. But as long as we know to avoid saying weird things like this, it needn't be the source of any serious practical problems. And again, this is very like the reason why we continue to do set theory naively rather than axiomatically. Russell showed us that to do things really right, we have to proceed axiomatically, using the axiom of comprehension to make sure that we don't go formulating these weird paradoxical sets. But the other way is just to use human judgment and don't go formulating those weird paradoxical sets. Finally, Gödel's theorem implies a limitation that is in some ways more interesting than the incompleteness result itself. To see this, let's call our metamathematical system S and represent if CS then IS as saying that if the axiomatic base S of the system is consistent, then S is incomplete. This, of course, is just the central result of Gödel's proof. What's interesting is that there is a representation of this very statement within the system itself. Specifically, CS, the axiomatic base of S is consistent, is represented by the statement that there is a formula in S that cannot be proven, right? Remember that in any consistent system, there has to be something that cannot be proven, because in an inconsistent system, everything can be proven. So we could represent that, again, cheating, in our object language as there exists an X such that for all Y, it's not the case that Y is provable in X. Excuse me, I mean there exists an X such that for all Y, it's not the case that Y is a proof of X. So on the other hand, IS, which says S is incomplete, is represented by U, which says that there is a true unprovable formula in S. So since the statement, if the axiomatic base of S is consistent, then S is incomplete, if CS then IS, can be represented in S, it follows immediately that S itself can never have the resources to prove its own consistency. Now, if you can see why that is immediately, then congratulations, because that shows a lot of insight. But the fact is that the reason is really simple. And it's kind of a nice way to end the course by coming back to the most well-known derivation rule of all, modus ponens, or what we call conditional elimination. And so we just note that if a system S has the ability to prove its own consistency, that means it can prove that CS is true. And if we can prove that CS is true, then it follows by modus ponens that IS is true. But remember, IS is just a way of representing the existence of a formula that says of itself that it cannot be proved. So fundamentally, if we can prove, if a system has the resources to prove its own consistency, then it would actually be able to prove the formula that says of itself that it cannot be proven. So the reason is disarmingly simple. If CS were provable, then IS, which is just to say would follow by conditional elimination. This would be a proof of a statement that we have already established is unprovable, assuming S is consistent. So just as Gödel's incompleteness result does not imply that there are truths that can never be proven, the fact that a system representing arithmetic cannot prove its own consistency does not mean that arithmetic cannot be proved consistent. Arithmetic has been proved consistent, but only in systems whose own consistency is just as open to question. So the philosophically interesting suggestion here is that to know the consistency of a system of thought we must always occupy a perspective beyond it.